I'm a senior engineer in KCB. We call it KCB in short. And I mostly lead the analysis of dams. We do a lot of analysis of the existing dams in BC because of seismic retrofit. BC Hydro has a lot of seismic retrofit projects, huge projects, because most of the dams in BC were built order of 50 years ago, or a lot older than that. Therefore, we study them one by one. We propose retrofit. Even in one case, we propose demolition. So one of the dams are being or will be demolished in the next few years. And that dam was like 100 years old. And part of that study to decide about this retrofit and demolish is the seismic analysis, and we use finite element tools to do that. I guess this course is related to finite elements. Yeah, however, I have been working with Clone for about 4 years or 5 years, and I have been in the industry and in this line of work for 15 years. So working for a few companies, and I brought in some of the presentations I previously prepared for different conferences and even university presentations. So not all of them are related to Clone. One of them, I picked one from Clone, but the very first one is from one of my previous jobs about 15 years ago. So basically, this one in this presentation, I go through some of the experiences we had with modeling Panama Canal, third set of logs, and I will introduce it and then go through some of the FEA aspects. I don't know how much familiar you are with this project and with the country of Panama. You use a pointer here, or mostly pointing because people know about the Panama Canal, which is in the country of Panama in like the central continental America. And the Panama Canal, the original Panama Canal that goes from, on the lower right side, you can see the Pacific Ocean. It's counterintuitive. On the other side, you see the Atlantic Ocean because the shape of the continent is a little bit awkward in that region. And goes from one side to the other side and cuts the way for the shipments. It has been there for now more than 100 years. And back in about 2005 was that time, they figured that they can increase the capacity of this canal. This canal was built about, as I said, 1940s, 50s, about 14, 15, about that time. And the size of the lock system there was for older ships. However, nowadays they wanted to accommodate larger ships that go through the canal. So, and like here you can see a schematic of the canal lock system. So you can see in that region that there is a lake which has fresh water in it, and its elevation is higher than the ocean on the two sides. And therefore, the ships should go from the ocean level to the lake level going through the lock system. And some of you guys already know about how the lock systems work. The picture on the lower left shows the schematic of what was proposed as the new lock system for the canal. And yeah, some of its features that helps with wasting less water, because every time the lock system works, some of the fresh water goes to the ocean. That one is shown in the lower right. I will expand on that a little bit further in the following slides. And Yeah, again, as I said, continuity, the other side is the Atlantic side. This is Pacific side, and that's Atlantic lies from the Pacific. The Pacific ones here. The city of Panama City is by Pacific Ocean. This picture shows the new life system versus the old, what was considered existing at that time, but now they are all existing. And so I mentioned 26 meters elevation difference that it should account for, like move the ships up and then down on the two sides. And yeah, I think that was a little surprising for me was that Pacific Ocean is 20 centimeters higher than Atlantic Ocean. But that's an interesting issue. Again, why they use this? The top left shows the previous, or I mean, both are functioning, but the older one is called the older. The older one, which was like the measurements was for older ships, which were smaller. And one of the reasons for the project was to accommodate the ships which were called post-Panama, which were like longer and deeper and wider. So that's one reason that they wanted those ships to go through the Panama. That's what.
So Ali, the ships go back to the previous slide and the one after this. After forward, go forward. So the ships come from the top to the bottom and they stay there. Like, how does it work?
No, both of them work in both directions. So maybe they alternate, like they take one ship from the lower elevation to higher elevation, and then next ship from upper elevation to lower elevation.
So it works both ways.
Yeah, that's my best understanding. Yeah, when I visited the previous canal was functioning, so I have seen that, but the new ones I haven't seen from. I haven't visited the new ones functioning, which have been functioning for 7-8 years now. So this picture, I think this one is like a real, like the MOP's rendering. That's after the new ones that are functional. You see that the ships are moving in the new canal. And so, as I said, they use the fresh water, which is the fresh water of Panama City and country of Panama. That's why there is reason to use less. And how much old lives we're using, that's important. And therefore, they had some reason to reduce the amount of water that they were using. And that's the reason that they kind of innovated those basins, those small basins. I will show you in the next slide that how they help with reducing the amount of water that is wasted. Yeah, so this one very nicely schematically shows why those basins help with reducing the amount of water that is wasted. There are connections, there are outlets that connect into the three basins. So when they are reducing the elevation, the water from elevation, like those columns shows the elevation of about 1 goes back to A, so it's not wasted. Elevation of 2 goes to B, so it's not wasted. 3 goes to basin number C, basin letter C, not wasted. The 2 bottom ones are flushed out, so they're wasted. And when they are raising the water, they bring back the water from C and B and A in that order, but they have to use fresh water for the 2 top ones. So instead of filling the chambers with 5 amount of water, 5 number of volumes, they use 2 number of volumes. And that's why they have 60% reduction in water. That was a very nice innovation for this new canal. However, they couldn't indefinitely increase the number of those basins because it would become expensive. And yeah, there's some information about how the project was run. I already forgot a lot of those. At that time, I was working with Rasekh. Second line talks about the designers, which was led by CICP, was representing the Panama Canal, and the MWH was basically leading the consultants, and Rasekh was the secondary partner of the partner with MWH. And there were some other players there. And they wanted to reduce consumption of water, that I already explained. And had tight specifications. It was monitored by some international experts and professors, etc. That's actually one reason that I like to present this work, because it was a high quality work generally for international projects, especially. And they had a good quality management system, which you guys should be familiar with or become familiar with, because it will work in industry, every work needs proper preparation, proper checking, proper independence review. And in Canada, we try to enforce this as far as we can, but for this international project, the client was very serious about quality management as well. And I think that figure is the final cost. Initially, it was supposed to be 20% less, but it costed about $5 billion. And yeah, that's the exact date. So 2016, it was in service. Now, that's the area that was mostly my expertise or my contribution. We did a quick evaluation of the concrete structure. The lock system is the concrete structure. And we were interested in the chambers. That's where the ships stop and then go up or down. Those are chambers. Vent walls are that end portion that opens up on the right or on the left. And the approach structure is narrow structure here that basically helps with moving the ship in the right position. And today when we arrived at Victoria, Sydney port, and they have a smaller size of almost the same structure, very small wing wall and some tubes that help with the ship not hit the walls. So same concept, but for much bigger masses here. Yeah, so I noted that this is not real, this is rendering, and it was before construction.
Excuse me.
Yeah.
You mentioned that there's a difference in the elevation between the basin level and the free water level, right?
Yeah, so yeah, primarily between, if I go back,
I mean,
that's what,
Yeah, so how is it done? How doesn't the water flow from one?
Oh, there are
elevation to
gates. You see those, you see the gates in there?
another? Okay,
So they
Yeah.
close the gates and then
Yeah.
they fill it up. And then-
Yeah, that's the way a navigation system or a lock system works, is that the ship goes into a chamber, the gates are locked on two sides, and then they pour water in there, and then the ship raises, and then they open one of the gates, which on the higher side, and the ship goes to the higher side, and they repeat this process 3 times until here, I showed I think it was more than 20%, 20 meter elevation gain.
Is this system using some pump systems or?
No, just by water, we fill it, and
Mhm.
because the ship is floating at the surface of the water, it's,
It goes
it's,
up
a
and
chance, it's
Yeah.
it is like an elevator,
Yeah.
but you use just the surface of the water by
Yeah,
increasing
yeah.
the surface. The ship is always floating at the subsurface.
So it's it's as you say, I think using pump system will make it too expensive. So most of the life systems, only water flows by gravity. And say if this side, like this is like, so if the near side is ocean, the far side is the lake. in the middle of country of Panama. It should go up from the ocean side to the lake side. However, because the water only goes by gravity, we are losing fresh water coming from the lake, and that's the fresh water of the country. So we want to minimize waste of fresh water. And yeah, those are some of the photos I have from that time. Our design team in Tetra Tech, which was in the Bellevue office, Seattle, and maybe when I was still working there, the construction was progressing, but was not final. Then I moved to another company in Vancouver. So those top pictures are like the large system under construction. Now suddenly jumping to seismic stuff. I don't know how many of you have taken courses about seismic structural. In seismic structural and even for buildings and for any structure that we study for earthquake, basically, the engineering process starts with recognizing the hazard in that area. And so we ask the seismologists, I mean, I use that term seismologists, but most of the time they are like good geotechnical engineers. We ask them to provide us with design response spectra. And the two curves that I have shown are the design response spectra. On the two sides, because I showed two logs, one on the Pacific side and one on the Atlantic side. So there were two log systems, and surprisingly, and these are, like if you look on the map, they are very close, but surprisingly, at least to me, still surprisingly, they have very different response. But
How far they were from? Like these two lines that
like you could drive from one to the other in 1 hour.
1 hour.
Yeah.
So maybe like 10
directly
kilometers?
50 kilometers.
50. So in 50 kilometers, you have such a different
Yeah, but
seismic.
yeah, I mean, interesting. Even in that 50 kilometer, the Pacific side is very strong, and Atlantic side is not as strong.
Just like Victoria and Vancouver, that Victoria is more
Or
seismic.
just like going from Vancouver to Montreal or something.
Yeah.
Like you change that. Yeah, but,
Interesting.
50 kilometers.
Interesting.
I don't know how many of you have taken courses in earthquake engineering. So like if you look at the plot on the left, I can explain it, which is Pacific, and then the right one is very similar. I have shown two curves. One I have called 475 years, and the other one 1,000 years. So one is for the earthquake and re-asking or the seismology, this happens once every 1,000 years. And the other one is the earthquake, or if I tell that, you will say that you are naive, but I just say that. Once every 1,000 years, the other one once every 475 years, and obviously the stronger ones happens less frequently, so the one in 1,000 years like higher. And so the horizontal direction shows the period. Like this diagram tells you what response you expect for a structure with a certain period, which is on the horizontal line. So we try to assess the period of your structure using finite element or time calculation or recommendations by, say, National Building Code of Canada. It gives you some recommendations for the structures. You find the primary period of your structure, and the vertical is the acceleration, which is an indication of the force. So you can almost think about it in terms of force, in terms of period of your structure. So starting from the very left, the structure is very rigid. It has very small period or high frequency. And then the period of the structure becomes softer. Normally when the structure becomes softer, most of the curves are like that. A little bit softer means a lot more force. So it absorbs a lot more force. However, when it's really soft and soft, like for tall buildings, high rises. Primary load. I shouldn't say the load decreases, but the load per unit mass decreases. So that's acceleration multiplied by mass is the load. So the structures of certain periods, they absorb the maximum amount of force. Which there is between 0.1 and 1 level. Normally it's 0.2.
So what is the typical period of the dams or the canals that you analyze in this project?
For different projects that I will present are very different. So for shorter dams or this one, it should be less than 0.1. Maybe if I get there, I have a
Okay, you have it.
taller dam, which would
Awesome.
be like close to 1.
Oh, wow.
Yes, it's like less than 0.1 to 1.
Okay.
Yes, it's the same aspect, right? 0.1 on the lower side, getting to 0.2 on a very high force, 1 which gradually reduce.
Okay.
And I mentioned the 2-level analysis design. That was also important for us as a good engineering concept. You do your analysis for 2 levels. Levels, you have the 475-year return period and 1,000-year return period, and you have different expectations from your design. So that is a very good concept, especially for dams and navigational structure. But I'll get back to it later on. Scale to the response. So that's another thing that geotechnical engineer provides us. Basically, what and I mean that's the procedure that keeps on repeating most of our projects. So I think it's important to introduce the work that we do. Then the geotech, or sometimes the structural as well. They use that spectral response that is specific to that region. And they try to find a number of earthquakes that can in a way mimic the earthquake that will happen in that region. And they look at magnitude of earthquakes, faults, distant rupture, the site characterization, like quality of rock, etc. To find some representative earthquakes which are very similar to that site of interest. And we basically use those earthquakes, the real earthquakes that happened for our analysis. However, we scale it. Like we scale it so that the response is what they have determined for that site. So like multiplied by 1.9. That's a simpler one that I have used, but the geotechs use even more advanced. They spectrally match it at those fancy things. But the main concept is to increase or reduce it to match the characteristic of that region.
Excuse me,
Yes.
which code was used for this analysis of this dam? Which, according to ASC, for example, is
Like
or
we use mostly international codes, and we normally provide what we call design basis. So when we provide the design basis, we read a bunch of codes and then summarize it in there.
yes,
For this one, we
because
have
it's a dam, not a structure.
So in short, I should say in Canada, the most important one is what we call CDA guidelines, Canadian Dam Association guidelines.
Mhm.
It's very brief, so that's the maybe if you want to know one code about dams, that's CDA
So
guidelines.
it's not,
But it's a good document. It's a very good document, although it's short and has 7 or 8 appendices. One of them is mostly a structure.
good to know.
Yeah. And I come to quickly introduce this concept as well. We don't want to go much into the details. However, let me displace go one more and then come back. So you see that here. Here I have shown, going into the fact that I don't know how much you have advanced in your course, how many sessions you have so far. You create a mesh of the structure of interest, which are those large systems on the top showing the Thomas Black. And the bigger greenish thing is the foundation, a chunk of foundation that we included in our model. And the red ones are soil, the soil backfill in there. And like the lighter green, the beige one is again rock, but the rock which is close to the dam, which was modeled probably more than there.
So let me see if we understand this. So the bigger section is the foundation.
Yeah, the
Right.
big one is foundation. So we include good amount of
The
foundation in our
and then-
models.
The next level is more refined mesh of the foundation, or is it the soil?
Yeah,
beige
we,
one.
we separated them because when you are closer to your structure of interest, you use better mesh.
Yeah, refined mesh.
And sometimes, like not in every case, but then sometimes say you want to account for nonlinearity.
Mhm.
But if you like every nonlinearity slows down, so you just keep nonlinearity in the area of interest.
Okay, so you can, essentially those elements has nonlinearity, while the other one, the bigger one,
Mhm.
is linear, because you are far from
Yeah,
the point of interest. Awesome.
some of them, like for concrete is linear, concrete model was linear. Water model, at least in our firm, we use what we call acoustic model, which only accounts for pressure waves
Mhm.
during the earthquake. And the soil was definitely nonlinear, like more columnar soil. Had to be.
And on top of the soil,
Mhm.
there is one layer of elements. What are those, like the white elements?
I don't know, maybe it was overburden showing in a way. Or, yeah, or maybe, yeah, yes, like after many years. Like when you use nonlinear material, the surface element misbehaves, so you keep the surface elements linear. Maybe that's what
Oh.
it showed in a
I didn't
different
know
color.
that.
Yeah,
That's
yeah,
interesting.
you don't want to be distracted by some node jumping up.
Oh,
Because it doesn't change the
interesting.
outcome. But maybe not, but maybe it was just overburden within that. And so this USVR guideline for nonlinear analysis is like one of the best guidelines that I use as US Bureau of Reclamation. I keep on using that.
US Bureau of
Reclamation.
Reclamation.
Yeah, so they have some good guidelines, like dealing with dams generally, and they have the guideline on nonlinear analysis of dams. That's one of my go-to short book. You just open and find something, and then if you want to study in more detail, I'll do it later on. Why I said based on that guideline, it tells you what dimensions to use, like H is the height of your structure, it says go more than 2H down, 3H on the side, etc. As the title said, I mean, I remember that this was a 3D image, it's a 3D image, our one element thickness or two element thickness. The analysis was to be intended to only study the sideways and up and down.
And so what is the depth of the mesh? Like we see the cross section of this.
Like,
How
just like I guess,
You
like
assume it's
this was-
infinite, like it's just one layer of elements?
Yeah, like this for the analysis only one layer was enough. It
Okay,
doesn't really, we didn't model moving in the
okay.
other direction. In terms of types of elements, yeah. And the type of elements, normally we prefer based on experience, and some of the times I do some tests. Hexahedron has the best behavior, like the best economy using less elements for higher quality results. So we normally try to be dominantly hexahedron, which I have shown. I pulled that out from the video or something. Hexahedron is shown on the shown it there on the top right. But then if you zoom in, because not all of them could be hexagon, you can see some triangles which are again cooled, and it's a prism actually.
And which software did you use?
Yeah, so the software of this project was already determined was Abacus.
Abacus.
Yeah, so there's an Abacus software. But normally when you have 3D, you even when you want to create a dominantly X mesh, you end up with all four types, hex and pyramid and tetra, etc. prism.
Mhm.
Normally, you prefer that it's like 90% X because the economics are like fewer number of nodes give you a high quality result. And the economy of the analysis was super important because the computers were slow at that time, but now you have much faster computers and cloud computing, etc. So we don't emphasize these things
Okay.
too much recently. We just say, okay, we tell me a mesh, and then we throw it at the cloud computing and just start crunching. So, and I want to go back to that slide. The earthquake records that the seismologists give us is mostly intended for the surface. They say that they call outcrop. Like, what is my earthquake at the top? However, for the analysis purpose, normally we apply at the bottom of this model, which is like 125 meters deep into rock. And we find to somehow guess or estimate what was the earthquake intensity at that depth that resulted in surface vibration that they provided us. And that was when this slide comes in. That we go through a process which is called deconvolution. In this style of analysis, there are other solutions which are going to meet this in gray. So basically, there's a fancy lesson. Too complicated, you want to know what earthquake at the base will result in the after that they provided us. And for the soil, it has a lot of meaning because a lot of things change, the frequency content change, etc. But for our case, we are concerned with rock, and only there is like an amplitude factor, like a few percent change, and we try to account for that. So that's one of the fancy things of, I don't know, fancy, but it appears to be fancy, but it's easy. And we have to say more close up of the structure of interest that we are trying to model and design. The wall of the basically the large system there, sections of the culverts went through, and some dimensions were used, so they are 30 meter high, typical.
So those squares in the middle, they are hollow. The water goes there, right?
Yeah, there are culverts that connect. They have a rather complicated water system that goes to those basins, from the lake to basin to chambers, and that's the pathway for the water. And mostly intended to save water.
And you don't use any element inside those squares.
If you want to, as I said, use acoustic models.
You still use acoustic model for those things.
Yeah, if I want to decide today, I mean, for water which is enclosed, only the mass of it is important. So somehow just account for the mass doesn't necessarily want to be acoustic. So basically, back to the big picture. Another close-up that explains better what was the material properties and material models. Yeah, as I emphasized, for the remote rod, it was mostly linear rod. For the closed rod, maybe some cases studies are more column, but probably it's not important. And the closed ones could be linear. However, the material we use the more custom. And I mentioned that the water was acoustic. Mostly. Okay. And yes, that's another kind of fancy idea there. Yes. So basically, we're gonna do dam analysis. Yeah, right.
We consider the variation in seismic low, for example, that's 400 meters length. The seismic excitation is not.
Spatial variation. No, I mean, number one is that this structure is small. I mean, I know that there are like some long span bridges, like one pier on this side of the canal, some canal, another one on the other side. A spatial variation is important because one pier moves differently than the other pier. Here it depends on how you model it. Like if you make it very symmetric, basically the waves will go up very symmetrically. Also, there won't be much spatial variation. However, if you make the geometry symmetric, there will be a little bit variation, but nothing that we care about or we plan for. Maybe it happens. So we don't plan for a spatial variation, but we can do it. If it's like a really sizable dam, we can plan for that. And I think it's again a good place that I explained the difference between the two types of solutions that are often used. Classically, like for many dams of the world that are designed, what we use is a concept that is called massless foundation concept. So in a lot of analysis, we don't account for the mass of the foundation. We only use it for elastic properties of the foundation, so that it gives a spring property. However, more recently, one reason is the more advancement in computer stuff, more talented people that know how to use this software. We try to do more realistic model and account for the mass of the foundation. And when you account for the mass of the foundation, the simulation becomes more complex because the real seismic waves are created in the foundation and they move around. So you can imagine that we are trying to push the waves to go into the system from bottom almost approximately uniformly. But when they go up, they hit the surface and they reflect or those kind of things. Like any other wave, they hit the structure and they reflect. And if you do the more naive way of applying the acceleration all around, it's called like a rigid boundary that you are applying displacements. And in short, what happens is that a wave goes up, hits the structure, goes back, hits another boundary, goes back, and it's trapped. And the reactions in the structure would be very large. Therefore, we try to use some sort of dampers. We calculate the values for those dampers, and we put them all around so that the waves that are coming out of the system just go out of the system. Yeah, go ahead.
Dampers that we used within dam systems or seismic buckets for dams?
Seismic retrofit projects. Yeah, like more recently, like let's say my main client with BC Hydro, they are very, very interested in this concept. So yeah, we should be aware of that and we should use them. Like the older methods that most they are correct actually, using massless foundation, then you don't need to worry about the wave reflection and you just apply accelerations all around and shake the system. That's a good solution. But this is more correct. And there's a second benefit is that a lot of times for certain dams, like taller dams, it's more optimized. It's like gives you lower stress.
This means like dampers are used within the dam structures themselves.
Oh no, they're not real dampers. They are those dampers mimic the infinite, like you have an infinite ground. And then that's basically, I can call it something mostly mathematical rather than real. So you replace an infinite zone with a damper. That's
in infinity, the waves can down because they can go forever.
Yeah,
but we cannot model the whole ground. So therefore, to replace that and simulate the damping effect of infinity, we use some virtual or fictitious dam.
That's a better explanation. So the waves that reflect from my structure damp because they go to infinity. But my model doesn't have infinity, so I calculate the damper for that. So that's a better explanation.
So one question, you said if we have these advanced simulation capability with this absorbing boundary condition, you're gonna have more realistic view than massless elements. And based on what you said, I guess, correct me if I'm wrong, for taller dams, the basic approach is more conservative because it leads to higher. So that's why the older dams are still safe because they used a very conservative approach.
Yeah,
The massless.
yeah, the existing dams in every aspect, they were luckily they were built very conservative.
Very conservative.
Because the estimate of earthquake right now is like 3-4 times as much as they use, but we test them and they are very good. So luckily they.
And have you ever compared like two different simulations, one with massless, one with the boundary condition, and quantify the error or the discrepancy between the maximum stresses?
Yeah, I mean, I personally have done that, like personal interest. Maybe one of my slideshows have one of them with that, but
That's
I
interesting
can,
for our class.
if we get there, I will show that. Yes, I have it because they
Please highlight that. Yeah, that's interesting.
That was actually for the very tall dam, for the 200 meter plus dam.
Yeah, that would be very
Yeah,
interesting.
I can show that to you. And for that dam, basically they had some model that started the process using ANSYS software, etc. But they were getting such a huge reactions that they couldn't design. And then that particular company didn't have experience with this solution. They said, okay, we'll learn this and we should implement it because this is not designable with the classic approach. But now in BC and the PCR, it's becoming like everyday process because they really like it. So they want to do the correct solution. Yeah.
When you want to design a dam, what are the concepts of, what are the goals of designing? For example, in buildings, we know that we design the members of the structure so that under the specific combination of loads, they're not failed. So what are the design criteria for a dam?
Yeah, so let's assume this is not dam, this is navigational structure, but even for this one, I will get there. I will give you the criteria. Then I will show you another slideshow about one dam. So again, the interfaces and what was the assumption about the different interface of water and wall. Mostly we are interested in friction angle and cohesion between the two. And almost all the time we overlook cohesion. So we are interested in the friction angle at different locations, like between the dam or navigation structure, rock, internal friction angle of the backfill, etc. These are data for this project. And yeah, so this is very important part of our documentation. We should really keep on emphasizing and even forgetting ourselves that the assumptions should be written very well and legible, and everybody should be able to follow it, because when somebody wants to judge your work 10 years later, he wants to know what was your assumption rather than what was your conclusion, or both of them. He wants to know both of them. So yeah, we keep on emphasizing, but myself sometimes forget to clearly write what was my friction angle, what was my concrete quality, what did I assume? Because sometimes the data is not available. We should assume something, but we should clearly write it for those.
So what is the basis of your assumption? Like, is there any guideline that what to pick, for example, for the friction between wall and backfill, or is it based on previous experience?
Important projects, international projects or Canadian projects, a lot of testing is done. So it's number one is testing. But even that USBR guidelines that I mentioned, that is my go-to, it gives you typical values. So if there is sometimes it's like a low budget project, you just some estimate. Or sometimes you do sensitivity, you say, okay, I don't have the concrete property, but I test 3 values and give you a result for each one. of those
Essentially, you
values.
give it bound for your result.
Yeah, so that they know no matter what is your concrete value, it doesn't matter.
Okay.
Yeah,
On the assumption here is the high condition between the wall and the slab. So it means that there isn't any related displacement between the wall and the slab. There is a connection between the wall.
Rock and
so rock
Rock
and
and
slab. All right, yeah, so if it's a tie, yeah, means that they don't move and they really tie them, they put dowels in there.
So,
Yeah, so they don't really move, Peter Spitzer just move together, so we don't, they don't, there's no movement, frictional movement.
so the logic behind the tie is because you use dowels,
Mhm.
so that kind of justify the assumption. of
Yeah.
the tie.
Like there is a friction angle there, but we don't care because they don't move with respect to each other, so. Yeah, so say that slab is narrow and water pressure will build up under it, so the main reason that you should use dowels is that otherwise it will be floating, so you dial it down, give it a go. Yeah, so I mentioned that as well, dowels tie down the slab. Material properties, we don't need to go through them. Yeah, emphasize again that always, like they mentioned, what is your material property, what assumptions you use.
So why the modulus for dynamic and static are different? Like, can you comment on that? Why it's higher, the dynamic modulus?
Yeah, physical reason is not on top of my mind, but then it's a known fact that,
No fact.
yeah,
Okay.
that for most materials, the dynamic modulus is greater than the static modulus.
Interesting.
Yeah. So that's a good point, and the guy can sometimes tell you like this one appears to be 30% more.
Yeah, it's interesting. For example, for the backfill moist, it's 10 times higher. The modulus. The bottom table for the backfill moist.
Right, yeah, you can imagine that for soil, if you push it slowly, it goes down.
Yeah, and
But if
there's
you really
interesting.
press it hard, it will stop you,
Yeah,
so.
because I've never modeled soil, so that was interesting. for me.
Yeah, that's not my focus on. I never really. Pay that much, yeah, that's probably- For dynamic work, we use the dynamic properties. And for concrete and rock, which are our main materials, it's like 20-30% more normally. But we get recommendation from the specialists that are just, that's only my rule of thumb, so that I know I'm not receiving something incorrect.
Yeah, that's very interesting.
Yeah, so that one is more like a damping issue, like.
Yeah.
Like when you go slowly, but when it's fast, it's like the damping is also resisting, you know, I mean, that's the main reason. 10 times. Yeah, so we should bring in a geotechnical specialist as well to the. Static forces are applied, and static forces, maybe they do some of it trivial for the chamber, how it's applied in the top layer and inside the covers.
Mhm.
So I think I pulled this out from what we call design basis. Before even starting the work, we write a design basis that we try to explain everything in a good amount of details, so that we ask new engineer to do it. We say, okay, exactly follow this guidelines, apply and for more international or important projects, it should be written very clear. How to apply your hydrostatic, no matter that a lot of people think it's trivial, but let's check it out clearly. And interface of the structure and rock, also there are some uplift pressures. They use simplified assumptions to apply other seepage of water going from one value to the other value almost linearly. So we basically hope that you have to calculate it and don't forget to implement it. So I think there was a question about periods of logs. Answer is here for this log system. In the horizontal direction, it was 0.22. softer than what I would expect. So my recent experience is with dams, but a dam of that height, 20-30 meters, is so chunky that it's very much better. But this is not chunky, so that's why it's more than I see recently for 30 meters structure. And obviously the Pacific side was more chunky because it sees a higher earthquake, so that's why the period is smaller. That and column. For vertical excitation, what is the main period that we see for vertical movements? In your five element code, you normally have a modal analysis tool that you can use and find out about the primary modes of the structure and primary period. That relates back if you want to have a quick estimate of what is the force in my structure, you can go back to that graph that I showed you initially and read the acceleration multiplied by mass, almost what is the load that your structure is seeing. And so the modal analysis is the typical tool to do that. But beside that, when the system is very complex and has nonlinearity, etc., we do something else which we call frequencies sweep. So we excite the structure with different frequencies to see which frequency causes a higher response, and that's like resonance sometimes. And questions.
TN do that for regular period, the TN.
Yeah, that's it's a natural, probably what you say, over something probably really that the most important figure. That's the most important figure. And another kind of created because we want, sometimes we want, or most of the time we want to know what are the dominant range of periods that are important for that structure, like our guideline at that time says go between 0.2 and 1.5.
And so in that range of 0.2, between 0.2 and 1.5, so natural periods are based on the standard.
That's about what will be the recommended is one of the symbols, maybe the LCE, maybe goes to that. And to say here, so that it ties back to what we say about softening, like it really goes that so that you show that very structure which was previously past the region. Here we accounted for that in another way. We increase it by 1.5. So you say here my range of interest goes to 50% more than what I calculated because it might soften up. That's also related idea. And go as far down as 0.2 because the other modes of the structure, other important modes of the structure are smaller. And damping is very important. So the tail of this, I mean, it's in every dynamic book, dynamic there, but then, be careful that you should assign damping to a dynamic analysis to account for like energy dissipation in the system today. And a way of applying it is what we call Rabi damping that most of the functional softwares can do. That's beside the point. Yes, remember that you need damping in your system to account for internal material dissipation, energy dissipation. Then, so there was maybe the best job in explaining. So what happened? Something is missing between. So we have that model created. We put it in Abacus software. Already which way we jumped it because details are in the book. So I was find out. And we run the time history with all those specifications. Now jump into one of the design criteria that we should want to look at is the stress distribution. And that's the easiest one to output. We look at the stress distribution in our structure of interest and also in the foundation. Say in the structure of interest, looks like we outputted S22, which is the vertical stresses.
So
And,
two is the vertical direction, right?
yeah, that's probably, yeah.
So you look at sigma 2,
Sigma
you see
2.
the-
Because it's a time history, time was 11.58, which we had realized that's like a big shock happened there.
Mhm.
It was large displacement at that time, so we assume that the stresses are critical at that moment. The second one to the right of that is the shear force, S2, and maximum principal stresses. Normally you look at those as well, because the maximum tension or compression might not happen in vertical direction. Maybe it happens in a different direction as part of your course as well. So that's more what you do in finite elements, and some similar outputs for the rock. And then you make your design decision. Is are my stresses too high? Are my tensions too high? My compressions are too high comparing with the concrete specifications that you have? Or if it's high, could it be justified? Like a red point, yeah, maybe it's a modeling issue, but it's only a stress concentration.
So Ali, in addition to concrete and the rock, is there any steel component here that may fracture?
Not that we analyze that, but this is a reinforced structure, so that's
Okay.
different than all other dams that I
Yeah.
work on. So this is a reinforced
And,
structure.
and how about those dowels that you use to tie the concrete to the
Mhm.
bedrock? Do you also check the capacity of those dowels that they may fail?
That's possible. You can do that.
But you haven't considered that in your
Maybe engineering judgment is that floating thing is the critical one. But potentially you can look at the stresses in that slab and see how much it wants to jump up.
Yeah.
And then those levels should hold it down during earthquake, during the force moment of vertical movement of earthquake. But the judgment or experience says that the flotation is dominant for the design.
Okay.
Right. And displacements are we normally control the displacements as well, like what is the relative all it means is that the top of the wall with respect to the bottom of the wall, how much it deformed in the worst time, it deformed less than 10 millimeter.
Is the limitation?
Yeah, like for this project, I will show you that. Yeah, the general rule of thumb is that 1% is very high, I think, but this is looks like less than 1 in 1,000 or something.